Hello and welcome to this calculus video. Today we'll be talking about related rates.
Math 112.
We have now all the techniques for computing derivatives that we will cover in this class. So now we are going to start applying the derivative to help solve some problems. Recall that the derivative measures the rate of change of a quantity. In many applications we are interested in the rate of change of one quantity, but it is much easier to measure the rate of change of a second quantity. If the first and second quantity are related by an equation, then we can use the chain rule to find our desired rate in terms of the rate we can measure. For instance, suppose we are blowing up a balloon for a party. If you've ever done this, you might remember that the radius of the balloon changes very fast when you start blowing, but changes more slowly as it gets more full. It will be reasonably easy to measure the rate of change of the volume of the balloon because we can measure the air we are blowing into the balloon. It is practically much harder to measure the rate at which the radius increases. However, the radius and volume of a balloon are related, and so we can use the rate of change of volume to compute the rate of change of the radius. Let's make this more concrete with some numbers. Suppose air is being pumped into a spherical balloon so that its volume is increasing at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? To solve a problem like this, we need to identify the known information and the unknown we would like to find. It is helpful to introduce some variables to represent quantities, often accompanied by a picture. We are given the rate of change of volume with respect to time. Because this is a rate, we want to express it as the derivative of volume with respect to time, so we need to name time t and volume v. We are interested in the rate of increase of the radius. This is also a rate, so we express it as a derivative. In this case, the derivative of r with respect to time. To connect dv dt and dr dt, we relate v and r. In this case, by the formula for the volume of a sphere, v equals 4/3 pi r cubed. We differentiate both sides of this equation with respect to t using the chain rule. We find dv dt equals 4 pi r squared dr dt. We can solve this for the quantity we want, dr dt, and plug in r equals 25, dv dt equals 100, and we get 1 over 25 pi centimeters per second. Let's take a look at a second example. A 10-foot long ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? First, let's draw a diagram of this situation. We see that the ladder forms the hypotenuse of a triangle. Let's name the base of this triangle x and the height y. With these names, our known rate is dx dt, and our goal quantity is dy dt. We need a relationship between x and y. In this scenario, x and y are the legs of a right triangle of known hypotenuse, so we can relate them via the Pythagorean theorem, x squared plus y squared equals 100. Differentiating this with respect to t gives 2x dx dt plus 2y dy dt equals 0. We can solve this for dy dt equals negative x over y times dx dt, so we need to know x, y, and dx dt. X is 6 and dx dt equals 1, as given in the problem statement. To find y, we use our Pythagorean relationship again, and find that y is 8. Plugging everything in gives us dy dt equals negative 3 over 4 feet per second. This quantity is negative because the ladder is sliding down the wall, so the quantity y is decreasing. That's all for now, folks. Today we discussed related rates problems, where we are given a scenario where we know the rate of one quantity and are interested in the rate of a different quantity. We developed a strategy of naming known and target quantities and using geometry or other known facts to relate these quantities.
Math 112.